This video, we're going to prove the integral test, which says that if an is a series of positive terms and that a sub n is equal to f of n, where f is continuous, that is, you can draw it without lifting your pen, and it's always positive, and it's decreasing. It's getting smaller and smaller, but always positive. And if this is true for all x bigger than some n, that is at some point, then both of these have the same answer. And this should say infinity. That is, either they both converge or they both diverge. Now, in my proof, I'm just going to assume that n is 1. Going to assume that n is equal to 1. Proof. Suppose the integral from 1 to infinity of f of x dx diverges. The integral equals infinity. Okay, so here's the function. It's decreasing. Here is where x is 1 and 2 and 3 and 4 and 5, etc. But that also corresponds to A1 and A2 and A3 and A4 and A5, etc. Now, let us look at this area. So now each base is 1. So every rectangle, the area is the base times the height. But if the base is 1 and you multiply it by the height, you just get the height. The area of each base is just the height. Now, since this integral diverges, that is, the area under the curve to the right of that line is infinite. It just is infinite. It doesn't converge to 3 million square feet. It goes to an infinite number of square feet. Okay. So, how about we use inscribed rectangles? That is, we have, actually no. How about we use upper limits? How about we use these heights? How about we use those heights? Okay. So what is the area? Okay, well, the first area is just that height, which is A1, plus this area, plus that area. But that area is A2, plus this area here. Well, that uses A3. This is A3, plus, etc. Okay. I mean, I could have said that this is f of 1 plus f of 2 plus f of 3 forever. Now, what do we know about this area? This area is greater than the integral from 1 to infinity because I'm adding this area, which is in under the curve. It's always more. So it's going to be greater than this integral, f of x dx, which diverges. And what we showed is that this infinite series, that is, the summation of a sub n as n goes from 1 to infinity, also diverges. If the integral diverges, then the infinite series diverges. And maybe I'll just say one thing, that one additional thing. That was case 1. Let's do case 2. Case 2. The integral from 1 to infinity of f of x dx converges. Okay, that means that from 1, that this area that goes to the right forever and ever and ever and ever, that gets smaller and smaller because it's decreasing, it has a finite area. So, here's a 1, and here's a 2, and here's a 3, and a 4, etc. a 5. Let me draw these ones as well. Now, we're going to pick the right endpoints. So, the first rectangle, its area is a 2. Remember, each base is 1. Because this not only, that's also 1 and 2 and 3 and 4. Hope you understand that part. That's a 2. Plus, the next rectangle, its area is a 3. The height is a 3, and the base is 1. So we get a 3. And then a 4, and then a 5, etc., etc. And this is equal to the integral from 1 to infinity of f of x dx, which is finite. This is finite. But you may say, wait a minute, you don't have all the terms. Fair enough. I'm going to add a1 to both sides, plus a3 forever and ever. That is the summation of a sub n, and then goes from 1 to infinity, is equal to that. And I'm going to add a1 to the other side. Now, this is finite. Okay, a sub 1 is just a number. We're also talking about it being areas, but it's a number. It's this height up here. It's that height up there. It's a number. The theorem should have said that we should have defined a sub n's. A sub n is a series of positive terms. That is, a1 is just some positive number. It's not infinite. So when I add a sub 1, which is finite, to this integral, which is also finite, the result is finite. That is, this result, this result right here is finite. But that result equals to the summation of all of them. Hence, the summation of a sub n as n goes from 1 to infinity converges. So, when the integral diverge, the summation also diverge, and if their integral converge, then the summation converges. Either they both converge or they both diverge. And again, the sequence has to be decreasing. And I'll say one more thing. They talk about after a special n value. What they're saying is, in terms of f of x, the function can be crazy. It can even go negative. I don't see why not. But after n, it has to be decreasing and always positive. Okay, what happens to the left when you add A1 and A2 and A3 all the way up to A sub n, you will get a finite number. Okay, when things diverge only at the tail end, because the finite ones, the finite terms, the first 50 billion terms, add up to a finite number. Okay, so after this special n, the function is decreasing and always positive. And f of n plus 1 is equal to a sub n plus 1, and f of n plus 2 is equal to a sub n plus 2, etc. So if this area diverges, that means that the summation as n goes from capital N to infinity of a sub n diverges, and when you add on the finite terms before, we can say from 1 to infinity diverges. If this converges. If this area diverges, then the area from, the summation as n goes from capital N to infinity of a sub n also diverges. So when you add on the summation from 1 to n minus 1, it'll still diverge. It'll diverge faster. Okay, I hope you understood this. This is a fun proof to do. I would love for you folks to leave comments about how you like my videos, or how you dislike the video, or if you know of a nicer proof, or you found an error in my proof, or you would like for me to do a proof that you would like to see. Just leave a comment. Most of all, watch and learn.